Every day's a challenge because everything we're doing for the first time. And so sometimes that can be a struggle and it can make your days really long, but it's always worth it because we get to be the ones that are doing it first, we get to figure it out together, and we get to be at the cutting edge of science.
Whenever you make a breakthrough, it lights up your entire day. I know that the work I'm doing right now will have a direct impact on patients in a very short amount of time.
I think we're all very focused on the patient. We understand that the patients waiting for these therapies are really in need. We're all very curious. We all want to learn and understand, and we're all scientists at heart, and this is what we're built to do. I think working with teams that are diverse and have people from different walks of life is really important. People from different functional areas have different objectives, and they bring different opinions to problems.
The people who work here are working here because they want to be here, because they want to be a part of CAR-T, they want to be a part of the revolution in this space. And so the people make us different, and because the people create the culture, that ends up differentiating us from other groups.
Every role requires a really strong sense of flexibility and adaptability because we're working in an ever-changing environment, but that's what makes our job exciting. If they're interested in working in a place where you can learn something new every day, then this is the right place for you.
Long term, it's moving towards a cure for cancer. We're not there yet, but with CAR-T and the innovations we're making, we're on the right track.
Hello and welcome to this presentation titled Cell Therapy Manufacturing Using Simio to Predict Bottlenecks. My name is Kirill Dobrodimov. I'm an Operational Excellence Engineer with Bristol Myers Squibb. I work in the Cell Therapy Network where I support our continuous improvement programs and strategic initiatives across our value stream. I am based in Summit, New Jersey, where we have a CAR-T manufacturing facility. Now, CAR-T stands for chimeric antigen receptor T-cell. This is a type of autologous cell therapy product that can be considered a relatively new technology in the domain of cancer treatments. And with some of the first products becoming commercially available over the past 1 to 5 years, there are relatively few frames of reference or existing models for CAR-T manufacturing. If you look at the overview at the bottom of this slide, you'll notice that the CAR-T manufacturing process actually begins with the collection of an individual patient's blood. From here, there is a one-to-one relationship between product and patient, with every step in this process linked back to that individual. At the end of this process, the finished product is actually delivered back to the same patient that we started with. In early 2021, we wanted to start looking forward to scaling up the manufacturing process and asking, what does the scaled up process look like on site? We deployed Simio as a tool to build a comprehensive model for mainly current and future production capacity so that we could reach as many patients as possible. Now, some of the top challenges that we faced are listed here, and they include variable arrival rates for that starting material. So there are numerous factors that impact how blood arrives at our site. This was a significant challenge in the model development. The process itself is a week-long production cycle with intrinsic variability, as well as significant touch time variability that we had to manage and collect data on. There's no batching for this process, so it's one product to one patient. The facility manufactures multiple CAR-T products that have their own unique properties and process categories. And there's a nonlinear flow of in-process materials and information. And that basically means that the process itself is not easily broken into a linear sequence of events. There are many probabilistic components, decision points, and complex interactions between the teams involved. So for our actual modeling approach, we started by collecting all of our assumptions and data and process maps, Excel calculators and spreadsheets, and put them together to build what's basically a conceptual model outside of Simio. And this would act as the bridge between the real world and the simulation model that we could always go back to verify our understanding of how the process should really work and, well, all the different relationships that are going to be built into the model. We used an iterative approach to continuously align with stakeholders on key assumptions. So basically, this wasn't one long development cycle from start to finish. This was many frequent development cycles within the past year to continuously deploy and align with stakeholders. We used a top-down approach, so the early versions of this model only dealt with the highest scaled units of measure, very basic stuff before we got to any granularity. And the initial inputs were all fixed and non-random. So this meant we were only running steady state simulations early on as we kind of understood more and more about the process and how the model should work. But over time, we gradually added layers of complexity and variation depending on the use case. One thing that became increasingly important was the visualization of data inside Simio. This allowed for instant feedback when adding constraints, when adding variation, when making a change in the model, and we could quickly then react to that feedback. And so I'll be focusing on dashboards in this presentation, and I have many examples where that instant feedback was very helpful. So before I get into dashboards, I'll emphasize this concept of the iterative approach, the iterative design process. So we embedded continuous improvement or agile management principles into these development cycles, which meant that we were frequently deploying and realigning and collecting data and then reiterating back on the model and adding more features or adding more complexity. And this really works when the understanding of the process, understanding of how the project will look at the end is very limited. And so I listed some strengths here and weaknesses. Some of the strengths, right, when you have a lot of uncertainty at the beginning of a project, this type of approach works really well. We have fast results, right? We deploy very quickly, very often. There's fast results, there's good feedback in this kind of cycle. And it's easy to change scope and pivot towards new business needs when needed. There's many touch points with stakeholders in that regard. But some of the weaknesses, right, this requires a low cost of deployment and use. It doesn't really work when it's very complicated to deploy a model like this. Generally, for each development cycle, that quick period of time, it's generally a narrow scope, and we could miss the bigger picture of why we're actually building this model. And some parts of the model do end up being rebuilt or scrapped over time, depending on the use case and what the pivot actually looks like for the model. And then we have some examples of how we increase the model scope and complexity over time and that top-down approach that I was talking about. So first of all, we have this high level, this high scale unit of measure. We're just measuring production volume, summarizing what production volume means for our facility. And from left to right, we're going from steady state to a more variable or dynamic simulation of just production volume, right? The summary of the outputs or throughput for our facility. And then we can break that down and go into major activities that add up to become the production volume for our facility. And again, from left to right, we're looking at steady state to more variable, more dynamic, more optimized distribution of events. And these are all built in dashboards, right? Which we will go over in the next slides. The last example here, right? We break down the major activities into further subcategories, which we're calling here the supporting activities, or we're just drilling down into resource objects or resource utilization inside the model. And so from left to right here, we're zooming in actually from looking at an average across a week for utilization of a resource to looking at the actual demand for that resource over time at the scale of hours to days. So now we get into dashboards, and we have several examples that I want to highlight and some tutorials for how to put some of these dashboards together. Getting started, this is in the results tab in Simio, the dashboard reports on the left-hand side. Generally speaking, you're just clicking on that plus sign to build a new dashboard report or clicking on the edit button to change an existing dashboard. And you can make many different dashboards that have different views for what's in the model. So here's an example of a dashboard built into our model. What we're looking at here is multiple views of basically cycle times, and at the top we're highlighting the initiation process, a major activity in our process, and the dots representing the average cycle time for that process on a daily basis. In short, this is a very predictable process in this view, right? From one day to the next, it's the same average value. Now, what we're looking at here is before adding equipment constraints, it's a very predictable, very steady state simulation. We know how long that process will take from day to day. When we add equipment constraints, we can see that there is an impact on our cycle times, right? So For initiation, now we have a range of values, and the dot representing the average is still embedded into that chart, but now we see a larger range of potential cycle time values for that step on a daily basis. And we can instantly view that full range of cycle time values and make an assessment. Are there any trends over time in this simulated run? Is the amount of variation realistic in terms of this range? And how can we strategically minimize variation if the variation is a little bit wider or more than we would expect for the process? At the bottom left, we have grid views for the same sort of information where we're looking at minimum, maximum, and average cycle time values. And the red bars can show basically the relative durations between one major activity and the next. Some of the other components for this dashboard view include tab containers and filter elements, and that just adds versatility and interactivity to this individual dashboard. So we're looking at different major activity types at the top for the different tabs, and then the filter elements allow us to filter by week in this case. So we can filter out the warm-up period at the beginning of the simulated run, or specifically look at a range of dates that we want to focus on. With that dashboard example in mind, I'm going to go over some of the steps that we took to build this dashboard from scratch. And this approach can be applied to different other types of metrics or different types of outputs that we're looking for in the model. In this case, as a model entity enters a server object that represents a major activity, so initiation in this case, before processing, we're going to trigger process logic. Inside the process logic, we're using an assign step to assign a timestamp, basically measuring time now in the simulation, to a state variable stored on the entity moving through the server. So basically, we're storing the timestamp at the beginning of the process. And then we use a tally step or tally statistics property on the server's output node in this case to record the effective duration of the major step. So now we're looking at the difference between the end time and the start time of that major activity called initiation. Then we're going to go into dashboard view. We're going to create a dashboard and use the tally observation log inside the dashboard to actually create these charts. So we use the create charts buttons. We drag and drop the values, and in this case, I'm looking at over time. So the time is set to day, month, year. And there's different arguments and filters that we can add on top of this to look at different time scales, different parameters. But generally, this is how it's built for this dashboard. One thing to note is the hidden data dimensions that can be used to increase types of filters. So we can make a more versatile dashboard without actually affecting the formatting of the chart itself. And then we get into further examples. I like to use the phrase at a glance for these dashboards and examples, because with minimal effort, we can very quickly draw our attention to a specific subset of data that's coming out of the simulation model. And in the process of both developing and using the model for answering different questions, we can use a combination of dashboards and quickly understand what's actually happening inside the model. How is the model actually behaving? Without going into details about what this chart represents on the screen, we see that there is an irregularity, a spike in the data in this highlighted region. And so we want to look at, okay, if we change the filters, can we zoom in and look at what's happening in that period of time? And here we can quickly just use a filter element to blow up that 2-week period or 1-week period and look at, what was the variation of this data within that time frame. We could then just highlight these dates and use them as filters for looking at either the Gantt chart or a more comprehensive report or other parts of the model where we might see that, yes, we have bottlenecks or we have deficiencies in the model that we need to fix. But this allows us to quickly look at, where are the irregularities and what do they mean? So for this next example, we're looking at a deeper dive of information. We're looking at workstation utilization for individual workstation objects. So in the dashboard view, we have vertically aligned 9 workstations that represent individual workstation objects in the model. And there are three categories of information that are being displayed: the in-use time, the available time, and then there's this fixed cleaning time that we also want to have displayed. And so for the entire duration of whatever the simulation model is running, we're looking at percent utilization, in use or available, or this fixed cleaning time window. I'm using a process logic loop combined with this expression at the bottom to generate three different values depending on whether each workstation is in use or available or just unavailable because of that fixed cleaning time window. The loop in this case runs every 15 minutes, so that wait step allows us to use a timer event that runs every 15 minutes. That's appropriate for this context. But in general, what we're looking at in the dashboard is our utilization across all of our individual workstations. If we want to add to that, we can create one resource object as a dynamic pool of workstations where I can just run summary metrics on that individual resource object in conjunction with this deeper breakdown of these 9 workstations. And I can also auto-create the different resource objects in a data table. They have their own auto-created tally statistic elements. So all of this can be very quickly modified and quickly added depending on whether or not I want to add additional workstations, remove workstations, or add any level of granularity in between. Obviously, if we have 2 different objects representing the same thing, both of those resources or objects have to be seized at the same time via task sequences or whatever you have seizing those resources. Now, if we take the example from before that had an irregularity in the data at a higher level and apply it here to our workstation utilization dashboard, we see that through filters on the day of the irregularity, there was also unusual use of our workstations. Now, so much so that this could indicate either a flaw in how we set up the model, the initial input conditions, or it could represent a real risk in our manufacturing process that we would have to go back and mitigate. From here, we would run multiple scenarios to look at modifying the initial input conditions or modifying the variability of the process until we are satisfied with the result. We can also export the filtered or the unfiltered results out to CSV or an Excel file where we can reproduce and reformat the data for presentation purposes or for deeper analysis. Going further with our dashboard examples, we have on the right-hand side a grid dashboard that represents a list of all of the resources that are built into our model, as well as ranking them by their relative demand in the model. Now we're defining demand in this case by the number of resource hours used per day by the model. So if we're using Cs or just servers that are being occupied, that demand is then represented here. And to get to this dashboard, we're using a mix of output statistics and periodic statistics. This approach can be replicated for utilization. It can be replicated for resource waiting time or server waiting time. So we're ranking basically indicators of bottlenecks in terms of demand, utilization, or waiting time using this approach. And we can very quickly see what are our top resources that we might want to pay more attention to or build more constraints around or less constraints around. I would recommend the Simbit periodic statistics to get started for this approach. But then at some point, we would have to auto-create the output statistics and periodic statistics in a data table if the number of server objects or the number of resources that are getting evaluated in this way get very large. At the bottom left, there's a waiting time expression that just goes to show that the more versatile we can make these expressions and data tables, the more dynamic and malleable these models will be. And then one thing that wasn't so intuitive when using this approach is that the value that gets entered into the dashboard for this view at the right is the value change. That is the result to look at. That is the result to perform any calculations on. You'll see the customized calculation box at the bottom. I'm using a calculation on that value change result to get this number of resource hours per day. As a final example in dashboards being used for simulations, I wanted to look at a case where the dashboard can help lead into or support a conversation about optimization and debottlenecking. So the charts here are representing effectively the same information, only the time scale at the top is a 7-day window of time, and the time scale at the bottom is a 24 window of time. For each of these, we're using an hour-by-hour representation of how many operators or personnel resources are needed in the simulation at any given time. At both of these timescales, we see an unrealistic demand for these personnel teams. There's a massive peak between the hours of 7 a.m. and 11 a.m., and there's relatively no demand for these personnel resources in the simulation between 8 p.m. and 6 a.m. And while we still see some patterns between Tuesday and Saturday, we already know just at a glance that these are unrealistic demand curves that we wouldn't really have in the real world. Because in the real world, as much as possible, we would like to level load our operations and efficiently use both the workstations and our teams so that they are well balanced and using their full shifts for manufacturing processes. For visibility, I showed how to set up the chart at the top. So you have a combination of two arguments of time, the day of week, and the hour arguments. But otherwise, the setup is the same as we've represented in other dashboards in this presentation. Once we add structure, maybe a resource schedule, or maybe just constraints on the number of personnel that can be active at any given time for each team, we start to see a more leveled off curve, and we start to see the impact on both manufacturing processes and other workstations and other resources. And now we have maybe more realistic perspective on how resources are utilized or how the simulation runs at these timescales. But it also gives us feedback in terms of how can we further level out operations, or how can we further efficiently optimize our manufacturing processes from the perspective of both workstations and personnel that are going to be at those workstations. Furthermore, as we iterate through these different views and as we add constraints layer by layer, we can differentiate between artificial constraints, artificial bottlenecks that are just products of the way that we've set up the model, and bottlenecks that would probably be experienced in the real world given these initial conditions. Also, at these timescales, we can now start to connect with shift schedules and more granular levels of detail in terms of where people are located, where materials are located in a given time, and the flow of these processes in a more granular level of detail. And with that, I end the presentation. Thank you, and feel free to reach out for any clarifications or any questions you may have.
Well, thank you so much for a great presentation. If you don't mind, we have some great questions from the audience. I will start with the first one. How did you decide the model run horizon, or how long to run the model? Does it vary depending on the case?
Yeah, it definitely does depend on the case. As I said, with the process being weeks long, so it's multiple weeks of the process just to kind of get a picture of one production cycle. Generally speaking, for a solid baseline, we're running between 6 months to a year to get one scenario. But to minimize that kind of time waiting for the simulation to run, sometimes we're only running 5 to 6 weeks just to look at one production cycle, a couple of weeks of steady state production cycles. So it varies depending on use case, but when we narrow down the number of scenarios, we're talking about years of simulation time, or kind of the equivalent in the experimentation tabs, or the parts of the Simio model in experimentation.
Oh, thank you. You had some great dashboards in your presentations. We have a lot of dashboards questions for you, so I hope you're ready. Did you formulate most of the dashboards on your own, or were they created in part by stakeholder feedback and or requests?
So the majority of the dashboards that were built were strictly for development. So in the process of developing the model and trying to understand that connection between our process maps, or kind of the conceptual model, and the simulation model, these dashboards were created to just view the behavior of the model itself. And then they ended up being also doubled as useful resources to look at future state scenarios, or like we said, like predicting bottlenecks. So they were mostly designed for the development process, and then they gained that use over time. But there was some feedback in terms of the important metrics that we need, the key metrics that would show whether we're productive or not productive, or what a bottleneck would mean for the site.
And thank you. Like I mentioned, a lot of questions on dashboards. How did you learn Simio dashboards, and how long did it take you to become so proficient?
It was purely experimentation, just trial and error. So I went into the dashboard view. I just started clicking on things. I think it took me probably 3 or 4 months before I started to get um, good looking dashboards, I guess, in terms of usefulness, and not just boxes and charts all over the place. So yeah, 3 to 4 months of continuous trial and error in the modeling, and again, it was for development, so I knew what I was trying to look for, and I had a purpose for these dashboards, but the first many iterations of the dashboards were just very basic, very maybe not informative at first.
Yeah. Well, thank you so much, Kirill. We'll do one final question. Of course, it's on dashboards again. Uh, do you ever use dashboards within experiments? If not, do you use a single replication dashboard for validation purposes or actual decision support?
It's a very good question. Yeah, so dashboards I have not used within experiments extensively or much at all. The dashboards help me narrow the scope of the scenarios that I would then run in experiments. So when I get to experiments, I already know the set of uh, conditions are basically bulletproof in the sense of initial conditions and the different scenarios that I want to run. Um, and so at that point, I'm using either external tools to Simio, or just looking at those responses directly and not needing to use dashboards. But dashboards definitely help me narrow down the scope of the different scenarios. And for those single replication runs, I can also see a combination of scenarios very easily. And that's not to say I'm using statistical analysis on that, but it does show me the behavior of multiple conditions kind of running at the same time as well.
Well, thank you so much for a great presentation and setting the bar very high for kicking off Simio Sync. Any other questions, feel free to reach out to Kirill or myself, Eric Howard. If not, thank you so much again, Kirill, and have a great rest of your day.
Thank you very much.
This concludes this presentation. Please click on the back button to access the next presentation.